This video and the video series of all of the different types of forces and accelerations is the one for the what's called the modified Atwood machine. It's a full Atwood machine if things are allowed to hang freely on both sides under the influence of gravity. A modified Atwood machine has one object on a surface or a table or something. Once again, even though it may not look like in this video, we're assuming that this part of the modified Atwood machine is perfectly horizontal. So once again, we start by labeling all of our forces. We have a force of gravity pulling down and a tension force pulling up. Here we have a tension force pulling to the right. On this first example, there will not be friction. We will do another video where we throw some friction in here and we'll see how that modifies things. Once again, we have a force of gravity going down. Technically, we have two separate normal forces going up on each of these wheels, but we can draw that as one normal force going upward. We can combine those two normal forces together. I've not given you numbers for the masses on this, so we'll just put a couple numbers in here. We'll make M1 10.9 kilograms and M2, let's go 4.7 kilograms just for something to use. All right, so once again, we're assuming no friction in the wheels or anything, no friction in this pulley hanging over the end. So force of gravity is pulling down on this, and through the tension, that is pulling this forward. So if there is no friction, hopefully, obviously, this is going to accelerate downward, which is going to accelerate the cart to the right. The only forces that are going to cancel will be the normal force and the force of gravity on M1. Once again, even though these forces are in opposite directions, they are not necessarily equal. If they are equal, this will not accelerate. It will just move with a constant velocity. So what we'll do is we'll assume, first of all, that it is accelerating. If we happen to find the acceleration number is 0, well, then it's not accelerating and it has a constant velocity on this side. All right, but to start off with, yes, we've labeled all of our forces, and then we jump in and we start doing our equations. So F net, and we'll just do M2 first, is going to be the force of gravity minus the tension force, because we're assuming that this is I'm just going to use the positive direction, so to speak, in terms of the direction I believe the object's going to accelerate. I believe this is going to accelerate down, and so then we'll do that one is the one that's being subtracted away from it because it's going in the opposite direction, and that will be the net force on M1. The net force on M2, excuse me, this is on M2. M1 is the object up on top of the table. So that one is going to be actually just the tension force. Right? The tension force is the only one pulling this in a horizontal direction, which will, I guess since it is the only force there, it has to make it accelerate, right? So if this is accelerating that way, then yep, force of gravity here is larger than tension. How much larger, we'll find out in a little while. All right, so now I can just substitute in for what I know, and for most of these that we've been doing, right? Net force is mass times acceleration. That is M2. So it's 4.7 times the acceleration is going to be the acceleration of gravity times the mass, right? The force of gravity on this, which is the acceleration of gravity times the mass minus the tension. And on this object M1 up on the table, the acceleration, which is mass times acceleration, excuse me, the net force, which is mass times acceleration, is going to also equal the tension. Like most of these, we have two equations and two unknowns. We can just substitute this in for the tension and do some algebra. I'm just going to move that down a little bit so we can see what's going on. Here we go. So you can always rewind and go look at the picture again if we need to put things together. So we have 4.7a equals 4.7 times 9.8. Let me just turn that into a decimal now. 46.06 minus the tension, which is 10.9 times the acceleration, right? Because that is the only net force on that one. So if we take 10.9 times the acceleration, here's 4.7 times the acceleration. That's negative, so we add it to the other side, and we get 15.6 times the acceleration equals 46.06. Do a little algebra and divide. And we get 2.95. Yeah, we'll leave 3 sig figs on this. Meters per second squared. So that is the acceleration of both objects. Once again, objects have to have the same acceleration, being attached with the same string. Same conversation we've had on a few of these videos. If the string does not stretch, or if the string does not get slack, right, the acceleration has to be the same. And since it is the first object pulling on the second object, which accelerates it, right, it will have to pull that along, and they do have to have the same accelerations. So once again, we can just start plugging back into these equations, right? We can find F tension, because that's going to be 10.9 times the acceleration. And that number is 32.2. So that's the tension force, which is the net force on M1. Right? So that's also F net on M1. It is the only force up there which is making it accelerate. F net on M2, we have two ways of calculating that now. Since we have the acceleration, the 2.95, we can take that times the mass, or we can subtract these two forces. We should get the same answer either way. So let's do this. Let's take Fg, which was the 46.06, and let's subtract the tension, 32.2. And we get 13.9. Oops, sorry. Let me just zoom out so we can kind of see this whole thing. Makes the numbers a little smaller, but you'll still be able to see them, right? So for this, I used the equation I have right up here, right? The net force on M2 is the force of gravity, which was this 46.06 number, and subtracted away the tension, which is 32.2. And there we go, 13.9. If you also just happen to take 4.7 times the acceleration, 2.95 times 4.7, and do it that way, we get 13.865, which is also 13.9 newtons. So it's always a good way to maybe kind of double check it a couple of ways. Once again, the net force should be mass times acceleration. You can do that. Or you can also use the equation up here and do that, and just kind of make sure that you get the same number both ways. And we do. So once again, this one is not too complicated. As long as we have just two objects and one string, there's really only one overall force that is really causing the entire acceleration, and then everything else just comes from the tension in the string, which we can calculate relatively easily. And there we go. So that is a modified Atwood machine without friction. Thanks for watching.